Thank you very much. Here is the map. Okay. Sorry.
Okay. So this is the last lecture. Lecture 4. Motivic multiple zeta values and Galois action or coaction. Okay, so I'm going to give a very quick overview of what's going to happen in this talk. And then I'm going to, this thing's going to be a lot more technical than the previous lectures. Up to now, so far, everything's just combinatorial. There's nothing that's really happened. Nothing very deep's happened. Now it gets a little bit more subtle. So there'll be some general comments about motives that I'm going to keep extremely short. I'm going to do the absolute bare minimum. And then I want to get to the point, which is motivic multiple zeta values, and explain how we can try to do a kind of transcendental number theory, a Galois theory of transcendental numbers for multiple zetas. So the idea is to have multiple zetas with a group action. And then in the last section, I will try to just illustrate with calculations, and so we get some feel for how this works in practice. I can actually compute. Okay, so for now I'm just going to give an overview of what's going on, because it's kind of a long story and I can't do the whole thing in full detail. But what we had was 2 points, A, B, in 0, 1, corresponding to tangential base points of 0 and 1. And what we had was the Betti fundamental group, P1 minus 2 points. I'm just going to abbreviate it with a symbol. We had the Durham fundamental group, which does not depend on A and B. And the point is that they somehow lift to something which is motivic. So this is the motivic fundamental group of and so we have the Betti realization functor and Durham realization functor this way. So perhaps to clarify some of the questions, the Durham or Betti individually are not fully faithful functors on the category I'm going to look at. Together they are, but if you take, so if we're just looking at Durham, we lose a lot of information. And so this thing somehow was for us graded, and it doesn't depend on the base point. That's something that only lives in the Durham world. It does not live in the motivic world. But it's very convenient to work in the Durham picture and retrieve that extra information from the action of a certain Tanaka group. So what I want to say is that it's nice to work in Durham because things are highly simplified, but a lot of the features here are not motivic. They do not lift up here. And we already saw, in fact, that a lot of the independence of the base point does not carry over here. That's one example. Okay, so the first point is that this Betti and Durham are actually two sides of one coin. So what does it mean to say that we have a motivic fundamental group? It means that this thing, whatever it is, or rather, it's these things corresponded to rings of specs of rings of integers. So it's better to think of this, the corresponding ring of functions on that thing, whatever it means. And what it means is that this is in fact an ind object. It's fact a Hopf algebroid object, in fact, but individually this thing's a limit of objects in some category of motives. And the motives in question are called mixed Tate motives over the integers, about which I will say a little bit, but not much. Okay, so what? Then the point is, the next step is that in fact MT of Z is in fact a Tanakian category. So in particular, it is equivalent to the representations of a group that I'm going to call GM today. And this group is called the Motivic-Galois group of this category. As I'll say in a minute, what is a mixed-state motive can be thought of as just its de Rham realization, the end of this arrow, with this group action. That's why I've been working in this side so much. So by the standard, since it's representations of a group, what we get is this group, which a priori is very mysterious, is going to act on this thing. Sorry, de Rham. So recall this is just a Q vector space spanned by words. It's something very concrete. For all A, B, and 0, 1. And because everything is, this groupoid structure and everything we had before is algebraic, comes from morphisms of algebraic variety, and same for the inertia as well, this action respects and respects the groupoid structure. So groupoid structure, the inertia, and everything else. We looked at in the last lecture. So what is the picture? We have GM acting on. So I can write pi de Rham, maybe to be. I'll just write O pi de Rham. Right? So this Motivic-Galois group acts in some way here. But we already know that we already computed the automorphisms of this thing. Actually, perhaps, sorry, I'm going to erase this. I've been excused. It's totally equivalent. It just fits better with the notations. And so earlier we computed the automorphisms of this system. And it was called V. And since this action respects all the structures, it factors through the action of V. And what's the dual picture, which is the picture I'm actually going to work with, is the corresponding dual diagram on the ring of regular functions. So this which way do I want to? Okay, I'll do it this way. So the top line becomes, sorry, O GM. So GM is some group scheme again. So this is what we want to understand. This coaction is completely equivalent to this action. And we know that it factors through this. So my apologies, I'm getting myself in. It's like giving lectures after lunch a little bit. Brain takes a while to get into gear. Sorry. I want to write 0 and 1 here, not A and B. So I'm only going to consider the action on 0, on the piece of the groupoid 0, 1. Okay, so that now fits with all the previous notations. Right. And the point was that we computed the automorphisms of the entire groupoid, and V was isomorphic to 0, pi 1. That was the proposition of the last lecture. And so what we get here, I can replace O of V with O of pi 1. In other words, what we're trying to understand is this action of this very mysterious Motivic-Galois group, and we know that it factors through this coaction that's completely combinatorial that I gave all those formulae for. In other words, this IHES action or coaction, depending on which diagram, is going to give us information, but only very scant information, about the action of this group, this Motivic Galois group. In fact, it's a miracle that we get any interesting information out of this at all. But that's the phase. We actually get a lot out of this. And so far, up to this point, you should be saying, so what? I've got an object in some category with some that is Tannakian, so I have some group. So what? That doesn't give me any information so far. It's completely useless. The really important point is that we know the structure of this Motivic Galois group completely, and that it's actually a very small group. And it's the fact that there are these very strong constraints on the possible size of this group that makes this entire thing work at all. Otherwise, we just get nothing. Okay, so then, what can we do with this? So we have a group acting on this thing, which is iterated integrals on P1 minus 3 points. So what we've got is an iterated integral plus, but we can also act on it by this group. We don't know how, but it exists. And such a thing will be called a Motivic iterated integral. And in fact, we computed the iterated integrals from 0 to 1 on P1 minus 3 points. These are multiple zeta values. And the idea is that a multiple zeta value plus this additional action of this group is what I want to call a Motivic multiple zeta value. So what the upshot is, at the end of the lecture, we will get an algebra which was going to be graded. Let me grade it right away. Graded by the weight of Motivic multiple zeta values. And for now, they're just going to be symbols. So zeta n naught m with a little superscript m, just to remember that it's Motivic. So it's some object of some algebra that I'm going to construct. And so the weight, I remind you, the weight is the sum of the indices. So this Motivic multiple zeta value sits in the component of that same weight. Then on this algebra, it's going to have a Galois action inherited from the action on P1 minus 3 points. G Motivic cross H to H, which factors, so this is the key point, that this action factors through the IHES. We can compute it basically using the formulae I wrote down at the end of the last lecture. And it's another crucial fact is that it's equipped with a period map. Again, without this, we can't compute very much either. So it's going to be called period, and it's going to send the Motivic multiple zeta value, which is some abstract algebraic object, to an actual number, which is the same number as it should. And so this map is a homomorphism. So in particular, any identity you prove on the level of Motivic multiple zeta values automatically becomes an identity on actual multiple zeta values after applying the period. So the philosophy, for me at any rate, is that in this world H, we can do Galois theoretic computations on multiple zeta values, and then use them to deduce things about actual MZVs. So we do Galois. So I'll explain on some examples what I mean by this at the end. On Motivic MZVs. And then by applying the period map, we deduce information about actual MZVs. And the point is that this map actually goes both ways.
So when you describe this period map, you said you send this abstract multi-zeta value to its actual value.
Yes.
Is it known that that map has a kernel? Or not?
No, this is also, so conjecturally, this map is an isomorphism onto the space of multiple zeta values. So the whole game here is the art of doing Galois theory without knowing that these numbers are irrational. They could all be rational numbers for all we know, in which case none of this makes any sense. So an analogy is to think, imagine you wanted to explain to the ancient Greeks how to do Galois theory, and they didn't know that square root of 2 was irrational. So, Meno's slave hadn't been born yet. Then you'd have to work quite hard to construct a legitimate Galois theory where you didn't know this fact. And you can do it. You write down a number to be a polynomial defining equation and you can construct it. And that's exactly the game I'm doing here, except with transcendental numbers. And so the point is that also computations about actual numbers also go backwards and give us information about the Motivic world. Okay. So now let me quickly say some words about the Motivic background. So I'm going to go fast here because I don't want to overrun too much. And it's quite technical. So the Motivic fundamental group in a flash. Okay, so first I should say a few words. So there's this abstract category NT of Z. I'm going to describe very briefly what it looks like, but not how to define it. It's an enormously complicated construction due to a vast number of people. Cannot hope to do this justice in so short time. But all we need to know for this is that it's an abelian tensor category whose simple objects, but I will construct these later, are Qn, n an integer. And what else do we know? We know that the X1 groups in this category of two such simple objects. I could write mn, but it's enough to just consider 0 and n by tape twisting. And this is isomorphic to the algebraic K theory when n is greater than or equal to 2. Morally, if n equals 1, but something weird happens, which is why we're looking at z coefficients. So I'm going to kind of brush this under the carpet and just put 0 and less than equal to 1 to cut the story a bit short.
Can you remind us what is the value of the K-theory of Z?
I'm just going to give, that's exactly. So this is the whole point, that we actually know the K-theory of Z, and this is the really crucial, the absolutely crucial ingredient. So Borel computed in, so I didn't look up the dates, I think it's 77 and 78, two different papers, that the rational algebraic K-theory is isomorphic to Q if n is greater than or equal to 3 is odd. I'm not going to give the K1. It's a little bit more complicated. We don't need it, so I'm just going to cut it out. K1 is, of course, much easier to compute. Yeah.
N is odd or 2 n minus.
If n is odd greater than equal to 3, then it's one-dimensional. If n is greater than equal to 2, else.
Left-hand side.
Sorry?
N is the same as in left-hand side?
Yes. Are my indices correct? I think so. I think that's correct. Yeah, I think it's correct. Did someone say? No. I think it's okay. I'm being a bit quick here because I don't want to spend too long. There's K1 in here normally, and the whole point of mixed-state motives over Z is to artificially kill the contribution from K1. Okay, so the higher x's vanish. And so a better way of thinking about this is that it's actually a Tannakian category. And the fiber functor has a canonical fiber functor, omega. So again, they're different notations. Omega is the standard way to write this, but it's really the Durand realization. So I will write dr instead of omega most of the time. So, in fact, from now on. So MT, by the Tannakian, main Tannakian theorem, MT of Z is equivalent to the category of representations of this group, of some group, GDR. GDR is the automorphisms of the fiber functor omega. So maybe I should just put omega equals dr here. It's not ideal. Save some confusion. Okay, so there's this abstract category. What do we know? So the fiber functor is graded, so we actually get that G Durand is isomorphic to semi-direct product of a group U Durand with the multiplicative group, which grades the ring of functions on this, and in particular it's the algebra, and by the general Tannakian dictionary, the associated graded Lie algebra is isomorphic to a free Lie algebra, absolutely not canonically, generated by. So there's going to be exactly one generator for every x1, so which is one-dimensional for every odd integer greater than 3. So we get one generator in degree, and I'll put minus because I want my model to be positive weights. And so this is the translation of the calculation of the x1s. Borel's theorem says that we have exactly one generator in every odd degree, like this, and the fact that the higher x vanish corresponds to the freeness.
That means that it should be Kn and not K at 2 n minus 1. That was my question.
No, it's modulo 4. Because it's a totally real field, so it's modulo 4.
K9.
Yep. Sorry?
K5, K9.
Yeah. It's K5, K9. Yeah, it's confusing. There's always a doubling. Because it's a totally real field, so there's no imaginary places, so there's this gap. One thinks of it as going up in 2, but here it goes up in steps of 4. Okay. Right, so what is a mixed-state motive? A mixed-state motive over Z is a finite dimensional graded Q vector space call it M Duram, Duram realization of some motive, with an action. In other words, it's a representation of GDR. That's the same thing as a graded vector space with a representation of GDR. Okay, so the graded Lie algebra of this thing is something that's very concrete. Though in real terms, it's extremely difficult to know. There are no canonical generators of this category. It makes no sense. I mean, this is just some symbol. Only the abelianization of these things are canonical, and so in practice, it's extremely hard to compute. It looks like it's just a representation of something very concrete, but in practice, it's extremely hard to actually compute this action on any examples. So the ring of regular functions, which is what I need on UDRAM, is the dual of the universal, graded dual of the enveloping of this thing. Sorry. And this is what I will call this thing with the same notation as before. So this is the shuffle Hopf algebra with the deconcatenation coproduct. So this is the ring of functions on this group. So to clarify the question that was last time, this is the Q, the underlying vector space spanned by words, non-commutative words in these letters, but it's equipped with the commutative shuffle product. And each letter f2i plus 1 is in degree 2i plus 1. And it's dual to the corresponding sigma. Okay, so now let me give some examples of objects in this category, or how to construct objects in this category. So for now, it's a very abstract thing. What we know because of these extremely deep results in algebraic K theory, we know how big it should be. But there's no way to write down all the objects in an intrinsic way. That's completely, because the definition is very oblique. So all we can do is just to write down simple examples of objects in it. So let me do that and write down some examples of objects. So I'm going extremely fast here because the background is enormous and I need to get to the main point. So we can write down the cohomology of P1, H2 of P1, for example. That gives us the object Q of minus 1. Here's another object, H1, P1 minus 0, 1 infinity. In general, if you take the cohomology of some hyperplane configuration, it will define a mixed Tate motive over the field of definition. To be over the integers, it has to be very special indeed. Has to behave very well after reduction modulo P for all primes, and that's extremely restrictive. So there aren't many things you can actually do to write down mixed Tate motives over the integers. Here's one way. So I write P1 minus 3 points is of course M04, and M0n plus 3 is n copies of M04 minus the diagonals. And then we have M0n plus 3 bar, the Deligne-Mumford compactification. So this is some smooth scheme over specs, etc. So what you can do now is then take the cohomology of this thing. There's some leeway. You can remove a bunch of divisors at infinity, boundary divisors. In particular, they're defined over the integers. And you can take it relative to another set of divisors. And what you prove is that this thing, if you reduce modulo p for any prime, then essentially the combinatorics doesn't change at all. So the sort of the nerve of the corresponding simplicial thing that calculates this relative cohomology is unchanged modulo p for all p. And that's how you prove that it actually defines a mixed state motive over Z. So this relies on the fact that A and B are contained are boundary divisors. And the proof of this fact is due to Gontcharov and Manin. And it's one of the most general constructions. It is very hard to construct objects in here. This is one of the most general ones.
Could you give us some hint about what you have to do in order to prove something you write down there is a mixed state motive? Because it seems to be you're writing down some cohomology groups.
Yeah.
I mean, if it's a long story.
It's a very long story. Yeah. It's a long story. So because so if I write down a diagram of schemes over field of characteristic 0, then that defines an object in Voevodsky's triangulated category of motives over that field. Right. Then in Voevodsky's category, so you can look at the subcategory which things are Tate. So that means that the cohomology is basically built out of P1s, PNs, something like this. And then you have to extract from this an abelian subcategory. And in order to do that, you need to know something like this. You need to know some deep results, valence and Soulé-Vanchen conjecture. So empty Z is, the empty Q, the category mixed state motives over Q would be the image of all such possible diagrams of singular schemes, possibly, which are defined over Q, and which have some kind of restriction on the type of cohomology. Or it could be some subset. And so you put it in some huge pot of soup, and you quotient, and you take limits, and you do all sorts of categorical things. You completely lost the object that you started. I mean, there's no intrinsic understanding. And to say that Z is this question of being nice mod P for all P. So you have a functor that goes from varieties into this thing, but you don't have any feel for what. Yeah, so when I write a particular cohomology group, you're using a lot of facts about the fact that there's a abelian category and so on and so forth. Maybe, I don't know, maybe you will give more details about this next week. Okay, great. But basically the bottom line is that there's a way to construct objects in this category. And we know from Borel that this category is not very big. That's all that's going on. So here's a ridiculously fast way to sketch the definition of the Motivic fundamental group. So I take A, B in 0, 1 as usual, and I claim that this thing, the Motivic fundamental group is some subquotient object, I'm not saying which, of some cohomology of a compactified, of a certain type of partial compactification of the moduli space. And I take the limit over n, call it, for some way of including these into each other that I'm not going to specify. And so this is a limit of an end object in the category of mixed state motives over Z. And I'm saying that I claim that it's enough to take some very specific, so this is M0 n bar minus some very specific A. So a special choice, a universal choice of A, and B is some special choice as well. It only depends on n. So there's a way to write down some space that's some partial compactification of the moduli space. And its cohomology is enough to construct the fundamental group in one go. So this point of view, how to do this precisely actually hasn't been worked out completely. So the advantage of this approach is that you very quickly define this thing as a mixed state motif over Z. But you have some other things to show. You have to show that this thing is closed on the Galois action, and you have some work to do which has not been done. The traditional way to do this is in using a theorem due to Beilinson, and is explained in Deline and Gronshov's paper in great detail. Here you have some problems as well, because you have to worry about tangential base points, and it's a really fiddly story to do that. So there are advantages and disadvantages, and I think that the dust hasn't settled on the best way to present this. And if one had infinite time, one would sort this out. Okay. So now, let me now move on to Motivic multiple zeta values. So I apologize for being so sketchy on this part, but I don't want to get bogged down. It'll take a very long time to explain this in detail. Okay, so the upshot of this, you have to believe me, that what we get is this thing I've written down umpteen times now, isomorphic, the Q vector space bound by words and two letters. The point is that this isn't just an anodyne Durham for notational reasons. It is, in fact, the Durham realization of a motive. So for me, that would always be an ind mixed state over Z motive. So that's a highly non-trivial theorem, and it's a work due to a lot of people. So I'm just going to take this as a black box today. Anyway, so the upshot is that this thing we've been studying for the last 4 lectures now has this mysterious, but in some sense also concrete, we know its shape, group acting on it. That's what we gain. So the Motivic, in time-Motivic formalism, enables us to gain this action. Okay, so now, recall that an element in Q E0, E1, we were thinking of it as a sort of disembodied iterated integral, and it defines, if we integrate along the straight line path, it gives us a multiple zeta value, a linear combination of multiple zeta values. So what do we get? We get these things correspond to multiple zeta values, but we also have a group acting. So what we actually get is a function from U Durham. I should really take the Q points. Yeah, I've been a little bit sloppy. Okay, it doesn't matter. U Durham Q to R. So G maps to G omega DCH. So this group moves the words around in some way, and we can consider not just the integral of the differential form from 0 to 1, but the differential of its images under this transformation group from 0 to 1. And such a function is basically a Motivic NZB. So that's the very rough picture. So here's a naive definition. So this is the actual definition, but again, it's still a slightly naive point of view. So from the first lecture, there was the period map, which to a word in E0 E1 associated the integral along the straight line path omega. So this is lecture 1, and this thing is a homomorphism. So that was saying that the zeta, multiple zeta values satisfy shuffle relations, or the same thing that iterated integrals satisfy shuffle relations. So now I'm going to call this map PER, period. So now let Jm, right? So Jm contained in this thing. So this thing is the vector space generated spanned by words in these letters. In particular, it's graded. So I can take the largest graded ideal such that Jm is contained in the kernel of the period map, and such that it's stable under the action of this group. So what does that mean? So I want to think of this as the ideal of Motivic relations. Okay, so the objects of this are indexed by words. They correspond to some symbol which gives a multiple zeta value. I now want to, these things satisfy huge numbers of relations, as Hubert's going to explain next week. I now want to take the quotient by all these relations which are of Motivic origin. So what does that mean? So a relation between such symbols is Motivic if, first of all, graded, it's homogeneous in the weight. So I force this because I don't want relations between multiple zeta values of different weights. And in the case, there are none which are none. Then it's defined over Q, so I only want to write relations with Q coefficients. Then the relation has to be true. It has to be actually a valid relation between multiple zeta values. It has to be in the kernel of the period map, otherwise it's nonsense. And then I want not just that this relation is true, but that all its Galois conjugates are true. So it's a relation between MZVs which is true, such that all its Galois conjugates are true. And conjecturally, it's just the kernel. I would ideally just take the kernel of the period map. But we don't know that there are exotic, bizarre relations between multiple zetas that screw up this whole picture. We don't know that. So it's a real fudge to try to reinstate, artificially put in the transcendence side of the story whilst avoiding conjectures. So now so H, the algebra H is all possible iterated integrals on P1 minus 3 points modulo the ideal of Motivic relations. And because J is contained in the kernel of the period map, it has a map, period, to the real numbers. So let IM naught I1 be the image of the element I called I naught, EI naught, I1, which is an element in here, just a word, But let me write I Motivic to denote this element modulo Jn. In other words, in the quotient H, it acquires the superscript n. It's just the class in H. So what is zeta Motivic? N1 up to Nr. It's the corresponding iterated integral. And so from the first lecture, that was this particular, so I did this calculation. Right. So that calculation was in lecture 1. If I remove the m's, that calculation was in the first lecture. Okay, so and there's a better way to define these, which in fact is sort of much going back a long time, I think, but due to Deligne, possibly Bainson Deligne, which I vaguely mentioned in the first lecture in January. In terms of comparing two fiber functors, it's a better way to do it. But I'm not gonna go over that again today. Okay, so so properties. So first of all, by construction, this algebra H is graded because I took J by definition to be a graded ideal. So it's graded by the weight. And it's a Q algebra. The multiplication is the shuffle multiplication, again by definition. So let me say that again. So the elements of this algebra, it's spanned by the symbols IM, IN1, and they're equipped with the shuffle products, as always. Then we have the period map. I've already written it. So the period map sends this Motivic iterated integral to the actual iterated integral, again by definition. Sorry, I didn't give this notation, sorry. It sends this Motivic iterated integral to the integral of the straight line path from 0 to 1 of the corresponding word in one form. So I remind you that number naught is dz over z, and number 1 is dz over 1 minus z. Okay, so that's all formal. And then the sort of magic ingredient is this action. So I much prefer to work, so I will work from now on with the dual thing, with a coaction H to O u gram tensor H. Right, so the whole game is to try to understand something about this coaction. Okay, so let me recall yet again, the setup. So what we have is, in fact, so a priori we have U de Ram acting on one.
Is H self-dual or what
H is self-dual. No. I'm just saying something stupid. So I'm saying that if you have a group acting on a space, then I can write this as a coaction. Because to get the action from this is a function. So G of V equals delta. Call this delta of V, and then I do G tensor 1 like that. Right. So to every vector, you get a linear combination of elements in V and functions on G. You evaluate the functions on your given element.
Is it better to think of the right-hand side as functions from G into H? And then
This functions from D to Q. Yeah, so it's a standard thing in I don't know, in Waterstone's book or something on F1 group scheme. I can write this action. I have an action of a group scheme. I can write it as a coaction. So yeah, I keep switching between the two. Okay, so we have this thing acting, and what we know, we have no information about this thing. It's extremely abstract. All we do know from the previous remarks is that it acts through this group V of automorphisms. And we know that the group of automorphisms is isomorphic to 0 pi 1 by its action on 1. That was a calculation last time. So what this gives is this gives a map from O pi 1 to O of V, and then backwards to O U Durand. So formally we get a map from abstract iterated integrals to elements of the functions on the Motivic Galois group by looking at how it acts on 1. So it's just pushing symbols around, but actually this thing's extremely mysterious. And in fact, all the subtleties contained in trying to understand that thing. Okay, so now, so what do we have? So I want to use, we had this purely combinatorial thing, coaction, which I went to great pains to compute in many different ways last lecture. So this is entirely combinatorial. This is precisely all these formulae cutting segments apart. And then we have, I can take the quotient here, modulo all possible Motivic relations between multiple zeta values. So this gets very mysterious. And we have the Motivic coaction, which is the deep thing. And we know that this diagram commutes. So we know that I'm just saying that the Motivic coaction factors through this combinatorial coaction. So this is the true Motivic coaction. And what is the game we're playing? The game is to compute information about the true Motivic action from the combinatorial action. And again, it's a miracle that it actually gives anything at at all. It's kind of unreasonable that it actually gives you anything, any information. But it does. So I want to simplify this picture even further. And I'm going to by passing to infinitesimal coactions. So in the language of last lecture, I'm going to pass from this picture to this picture. And the reason is because I don't want to draw thousands of cuts of polygons. I just want to cut it once. So there's no information lost when one does this. So now I'm going to look at O pi 1 and this map that I called D last time, which is the left-hand picture. And so now on the left-hand side, I work modulo products. That's what the I means. And then this is going to map to H. And it's going to map in O of U Duram modulo products times H. So in other words, I want to understand how this group acts on these Motivic multiple zeta values. The game is to lift them up to these I symbols, draw pictures with polygons, and then come back down and hope that you've actually learned something. So let me remind you that I of U Duram is just the set of indecomposable elements. So elements of positive degree, this thing is graded. Modulo products of things of positive degree. Okay, but now what do we know? What do we know about OU Duram by Borel? We know that OU Duram was isomorphic to this this shuffle, what I call the shuffle hop algebra. So it's the vector space spanned by words in these letters with the shuffle product, and that's a commutative. That's a commutative ring. So what is no, that's not what I want to say. Sorry. It's not what I want to say. What do I want to say? I want to say it's co-generated. I don't want to say this. Sorry. Someone wants to say. Okay, fine. I don't need it anyway. So, yeah, fine. So we know this fact. We know something about OU Duram. Now, so let me recall what the formula for D was. So D, let me write D subscript K is the part of D where I only pull out sequences of length K. So it's a sum of I and just, this was the shape of the formula from last time, of subsequences of length K, tensor what's left after pulling out the subsequence of length K. So in particular, if if the action of all these operators is trivial, then the Motivic action, because it factors through these operators D, delta mod, is also trivial. So this combinatorial coaction doesn't necessarily give us much information, but what we do know is because the Motivic action factors through it, if it is trivial, then the Motivic action has to be trivial. Okay, so now let me do an example of such a computation. And let me compute the action on the single zeta. Right. Okay, so now I'm going to draw lots of polygons.
Now you're using Notch-Ross convention.
Am I, sorry, I beg your pardon?
You switch conventions. Wasn't one illegal in the first place?
Was it, what, sorry?
Wasn't one illegal in the first place? Should I read from right to
No, I'm always integrating from left to right. That's always been my convention from the beginning. I've always integrated from left to right. So you have to have one, to be convergent, you want one on the left. Yeah, I'm 99.9% sure that's the convention I used in the first lecture. I integrate from left to right. Right, so I just realized that, so all these things here, now I can put little m's. All these things are valid with little m's. Believe me. Well, it's actually by definition. So I'm going to use, I kept them up because I want to use them in the ensuing calculations. But in a sense it's sort of tautological because when I calculate upstairs and these things, the definition of the coproduct use these relations in it. They're not actual relations, they're the rule for the coproduct. Because when you pull out a subsequence that begins with 1 and 0, you're not actually in the right space. You're in O pi 1 0, and that tells you how to put it back into pi 0 1. It's not actually a relation, it's the definition. So I just put m's in case I write m's by accident. So now let's compute this thing. So single zeta corresponds to a 1 followed by a bunch of noughts ending in 1. Okay, so there are 4 types of terms. We can cut off a sequence that begins at 0, or we can cut off a sequence that begins here. Then there's a whole bunch of sequences where it's just somewhere that's interior to this long sequence of zeros. Let me draw in blue. And then there's a final sequence that's potentially interesting, that I'll draw in red, where it terminates in this 1. there are 4 different types. The first type, so I compute dk for some k of this thing, where length n, and so of course k is going to be strictly less than n in this. So the first term gives me sorry, it goes from 0 and ends in 0, and it goes 1, 0, 0, 0 in between. So we cut off this initial segment, and the remainder has only noughts in it, except the final one. I think that's great. Okay, so then there's the second cut, which begins at 1. And it's got just a sequence of noughts, and it ends in noughts. So that's this sequence. It goes 1, 0, 0, 0, 0, 0, 0, and then the remaining, after cutting off that segment, you get 0, 1, 0, 0, 0, 1. Then there's all these terms in the middle, the blue one, which is just entirely noughts. And the last one is this sequence here that goes from 0, ends in 1, and straddles a bunch of noughts, and then the rest is just 0, 1, 0, 0, 0, 1. Okay, so that's all 4 types of terms. But, but by definition, this is the duality action. Almost by definition, anything beginning and ending in naught was naught. So we can throw that out, for starters. Then any sequence naught to the R1 by shuffle product is just up to some factor. So the factor is one of R factorial. This is the shuffle product. And
Sorry, in your last time, why do you have 1 at the end? Are you sure?
where?
At the very end, shouldn't that be a 0? You cut off the 1 on the right hand side, so you left.
No. So it's this. So it's this thing. Oh, let me use a different color. I'll make a mess otherwise. So in green. So this is the last line. This is this segment here, and then I'm looking at that part there.
Okay. 1 is double. Yeah.
Yeah, but it's a different one from this one. Yeah.
The third one, 0000, but almost vanished, but 00, right? Third line, yes, 00.
0.
So only.
If it's length 0,
Yeah.
I'm not. K is bigger than 0.
So.
Yeah, I don't want to take. So the reason I only actually, so I've got to say actually, it only because Lie graded U is generated by the free Lie algebra generated by elements of odd length only. To understand, if I'm looking at the action of the Motivic Lie algebra. So the only thing that can happen is that I can compute the action of these guys. And these things have odd length only. So I only ever need to compute d2r plus 1 for r equals 1, for r greater than or equal to 1. Because the infinitesimal action of the algebra is, well, we know the generators only have degrees 3, 5, 7. So I never need to cut off a subsequence of even length. That gives me no information about the Motivic Galois group, and or length 1 or length 0. So in fact, I only need, in this calculation, it's enough to take k equals 3, 5, 7. So now that's, everything up to now is combinatorial. That's a deep fact, because I know that the structure of the Motivic algebra only has generators in those groups. And all the other information is completely redundant. So that simplifies, that makes calculations extraordinarily efficient. There's very little to compute. So in any case, yeah, this thing has length strictly bigger than 1, certainly. This is a shuffle product, and then, so this thing is actually 0. The integral of 0 is 0. This is the inertia, or the thing I kind of glossed over a little bit this morning. This is the iterated integral of dz over z from 0 to 1. It's log of 1. And this thing is 0. It has to be true. So this is the inertia condition. So that means this thing vanishes. So every time I have a sequence of zeros, it vanishes. So that vanishes, and this vanishes. Everything vanishes. So in fact, the action is completely 0. So it's nerve-wracking doing these on the board. You're terrified that it's not going to work out. But believe me, it works out fine. Yes, I think that's all correct. So of course, by reversing words, the same thing is true of. I've used the fact that this is also 0. Because by the last property, I can flip words. That's the definition. Okay, so but then we know that zeta Motivic n. So we've computed that the action is trivial. These differential operators that correspond to the infinitesimal action of the Motivic algebra are completely trivial. But the elements themselves are not trivial because the period of this Motivic multiple zeta value is the zeta value, and we know that this is a real number, which is non-zero. So the action is trivial, the object is not trivial. So what do we conclude? We conclude that the true Motivic coaction, acting on, say, an odd zeta value, is, well, there's nothing. All that remains of the coaction is just the trivial part. So I computed the part of the coaction for all weights strictly in between 0 and n. What remains is the piece of length 0 and the piece of length n. In other words, this odd Motivic zeta is trivial, is primitive, sorry. And we have to remind ourselves that the left-hand side is actually viewed as an element of OU Durand. So to do that, I'm just going to put some square brackets around that. Now let's look at zeta 2. And the same calculation says that the action is completely trivial. Plus, and I'd like to write the same thing, but of course, there is no component of degree 2 in this in the left-hand side. There's nothing in weight of length 2. So the class of zeta 2 in OU Durand is necessarily 0, because there is nothing in degree 2. So we've computed that. So in other words, zeta 2 and the odd zetas are primitive elements. So the corollary as an example of an immediate corollary one gets from this, is that these elements are algebraically independent. That follows immediately from the fact that they're primitives. Okay, so that was a first example of the kind of calculations that one can do. So to try and make things a little bit more clear, let me write down a model for the algebra of Motivic multiple zeta values, because it will clarify enormously what's going on. And then at the end, I'll just do some fun calculations to deduce some actual results from this. So, the structure of the algebra of Motivic multiple zeta values. So let me construct a model for it. So let U prime is this thing, and let me. You've noticed that the zeta 2 plays some special role in this story. So let me consider this algebra. So what is the basis for U? A basis consists of words in these odd guys, and at the end I put some multiple of f2 to the k. So the multiplication here is the shuffle multiplication for the odd guys, but the f2 commutes with all other f2 commutes with all f2i plus 1. So let's do a calculation. f3 f2 times f5 f2. So the f2's commute with everyone. It's going to give f3 f5 f2 squared plus f5 f3 f2 squared. So I shuffle together the odd index ones, but the 2's go to the end. Then there's the coaction. So this is just the torso version of the deconcatenation coproduct. So delta, let me write C of f of some such basis element equals, I just deconcatenate the left part in all possible ways and shove all the 2's to the end. So it's sum from j is 0 to r, f2i1 plus 1, f2ij plus 1, tensor f2ij plus 1 dot f2ir plus 1, f2 to the k. So it's just deconcatenation, but with this f2 here just keeps track of the weights, really. Okay, so now one can show, but it's don't have time to do it. It's not very difficult, but there is a non-canonical embedding from the algebra of Motivic multiple zeta values into this model U. So it depends on some choices, which is what I don't like about it. But it's nice because it gives you an intuitive feel for how many for the size of the space of Motivic multiple zeta values. So this map H, we can normalize it so that it sends. So I've computed, this thing is primitive, so I can send it to any primitive element. I'm going to send it to f2n plus 1. So think of f odd as corresponding to each odd zeta value. And zeta Motivic 2 is going to correspond to f2. And this map phi is going to be such that it's a morphism of algebras and also of algebra comodules. So I've done a lot of identifications here. Here, U prime, of course, U prime is the functions on U de Rham. And that's exactly what coacts on H. Again, there are a lot of choices in this thing, phi.
Missing primitives are primitives, right?
Choices are everywhere because, so I've chosen loads of things. Yeah, everywhere. I have to choose how to send every primitive H somewhere. There are loads of primitives.
Loads of primitives, yeah.
No, sorry, that's not true. There aren't loads of primitives. I have to.
You have to send that to a primitive.
I have to keep choosing primitives. Yeah, there's some.
Are the primitives just the S?
No, because you can have. Sorry, yeah, because there are loads of primitives. There are Lee words in the Linden words in the S and stuff like that. Yeah, of course, there's a whole. Fine, it's late in the day. And the blood sugar's something now. No, these are the only primitives here, but there's still lots of choices. First choice is that the fact that I've chosen these generators S, and I've chosen. Believe me, there are lots of choices. Yeah. There's also it implies a polynomial decomposition into zeta 2, and that's a whole other set of choices. Yeah. Okay, so this thing U is graded. So the degree of FA is A. And so I'm going to write U is direct sum UN. So now, if I write dn for the dimension of un, then it's an exercise to check, it's an exercise in counting words, that the generating series of dimensions is given by 1 over 1 minus t squared minus t cubed. Oops, I'm running out of time. So basically the exercise is that you compute the Poincaré series for U prime. It's something like 1 over 1 minus t cubed minus t to the 5 minus t to the 7. Because it's co-generated by those elements. And then you have to multiply by the Poincaré series of something with a generated even degree. So you multiply by whatever that is, 1 over 1 minus t squared. And you work it out and you get this. So corollary. So this is a theorem first proved by Goncharov and Terrasoma independently. I don't know which date. 2000. Which date was your theorem? What date was your theorem? The date. Which year?
What year?
Which year?
Which year?
Which year?
Each year.
2001. You don't know. Sorry. I need 2000, but I'm glad you don't remember. So what we get from that, from the fact that there's a canonical embedding, we deduce that the dimension of Hn, because it's embedded in U, is at most the dimension of Un for all n. But on the other hand, we have a surjective map, period map, and the period of every element here is a multiple zeta value. So in fact, we get a surjective map to the Q vector space bound by multiple zeta values of weight n. So in particular, the dimension of this space over Q is less than the dimension of this, and the dimension of this is less than the dimension of that. So that implies that the dimension of the space of multiple zeta values of weight n over Q is at most this integer dn defined by this generating series. And so this was a famous result, and it's conjectured by Grothendieck in some previous year. Okay. Right, so maybe let me just finish with a couple of computations along these lines to show how that we can actually use these this formalism to prove. So one sees immediately how the formalism is quite powerful, because the Motivic setup immediately gives you this very strong upper bound on the dimension of the space of multiple zeta values. But this can actually do a lot more. So let me just do an example computation. Okay, so let's look in weight 5. So U5 is a two-dimensional vector space spanned by F5 and F3, F2. And we know from the calculation I did earlier that we certainly have zeta Motivic 5, that's an element in H. And we certainly have zeta Motivic 3, zeta Motivic 2. And they're independent because they map to these guys. And since H5 is contained in U5, its dimension is at most 2. So in fact, it must be exactly equal to this. But on the other hand, we also have zeta Motivic 2, 3, which is another element in H5. So for abstract reasons, then, we know without doing any calculation that zeta Motivic 2, 3 is some rational multiple of zeta Motivic 5 plus some rational multiple of zeta Motivic 3 times zeta Motivic 2.
Zeta 3 times zeta 2 correspond to F32 plus F23?
No, because F2 commutes with everybody. F2 is commutative.
Is it?
So F2 never appears on. No. No, so F2 is just a device to keep track of the true weight. So think of this. This is a mixed state motive which has an action, a non-trivial action by sigma 3, but that is a weight 5, and the F2 measures that fact. So when I defined this here, the basis I never shuffle the F2s. It's just a marker to keep track of the grading. Sometimes this is just like the leftover GM action after taking the U action out. So I never shuffle the two. Yeah. Right. So we know a priori that there has to be a rational relation between these three things. Okay. So what can we do? We can compute B. So what we can do is apply an element of U de Rham, apply an element into the Galois group, whatever. Or more concretely, that factors through the action of some concrete decomposition calculation D. So what we can do is then, therefore, just apply D3. And so the left-hand side, we want to compute I of, so this translates 1, 0, 1, 0, 0, 1. And so let me draw a picture somewhere. Actually, I'll do it here. Oh, no, I'll keep that. I'll do it here. So let me draw this picture then. 0, 1, 0. Oops. 1, 0, naught, 1. It's not very symmetric, but it'll do. So what are the cuts that we can have? I want to cut off 3 things. Blue, like that. Red, I want to cut off 3 terms here, and then yellow, why not? Yeah, there are only 3 possible ways of cutting out 3 letters on this polygon. Okay, so what is D? So D3 of this thing, 1, 0, 1, 0, 0, 1, equals, so the blue term gives me I, 0, 1.
I'll give you 0 anyway.
Sorry, I've done something completely wrong.
Starting
Sorry, my blue one's in the wrong place. So this one, the blue one goes from 0 to 0, so as Herbert points out, thank you very much, that's 0, because I've drawn it in the wrong place. So what I wanted to do is 1, 0, 1, 1, no, the red one. Yeah. Oh, that's it. Those are the only non-zero ones. Yeah, so blue is 0. Sorry. My diagram is correct. I'm just getting tired. So the first blue arrow, let me write it out. 1, 0, 1, 0. This is vanishing, as Herbert points out. And I'll just compute the right-hand side anyway. Right, so next the red arrow. So that's 1, 0, 1, 0, 0. Tensor I 0, 1, 0, 1. And then there's a yellow one, which is I 0, 1, 0, 0, 1. Tensor I 0, 1. Not 1. Okay, so this is blue, orange, and yellow.
There should be 2 red ones and orange ones.
Beg your pardon?
Shouldn't there be 2 red or orange ones?
So this one is 0 because it starts and ends in 0. This goes 1, ends in 0.
But it could end.
This ends 0 and 1, that's it.
It could end in the other knot, no?
Not length 3. There are only 3 cuts of length 3.
Oh, length 3, sorry.
I'm only looking at cuts of length 3. There are only 3 possible cuts.
Yeah.
The first one is trivial, so there are only 2 cuts. So it's like there's almost nothing to calculate here. So then I have to work out what this means. So this ends in 0 and 1, that's okay. This begins in 1, ends in 0. So I have to flip the word. This gives me I 0, 0, 1, 0, 1. With a power minus 1 to the length, which is 3. Right? But then, what on earth is 0, 1, 0? But we have shuffle multiplication rules up here. So I can compute 0 shuffled with 1, 0 is 0, 1, 0 plus twice 1, 0, 0. Right? So the 0 can go in 3 slots. So here I've counted them twice. That means that I'll do the calculation in full. The shuffle product tells me that the product of these iterated integrals, or symbols rather, satisfy this equation. Right, so that's just the shuffle product formula. Again, this side is 0. So that means that this term is equal to minus twice. This is minus twice that term. So when I take minus it, it's equal to twice that term. And I add it onto here. The upshot is I get 3 times I 0, 1, 0, 0, 1 times I 1, sorry, 0, 1, 0, 1. And what that corresponds to, of course, by definition, is going to be 3 times the class of zeta Motivic 3 tensor zeta Motivic 2. Right, so now let's... So the left, if I apply D3 to the left side, I get 3 times zeta 3 times tensor zeta 2. On the right-hand side, we've computed D3 of this is 0. So if I compute D3, this gives me 3 times so this is really F3. And this gives me, because it's a homomorphism for multiplication, this. So obviously this implies that B equals 3. So is that, I hope that's not too confusing. So what we're doing here is computing relations between multiple zeta values, not by actually doing any relations at all, but just deducing relations from what the action of the Motivic Galois group would have to be on. So that means that zeta Motivic 2,3 equals some rational number, zeta Motivic 5, plus 3 Motivic 3 zeta Motivic 2 for some A and Q. And unfortunately, alas,
What's A?
A is some rational number. We don't know. We don't know that. So alas, there is no algebraic way, so far that I know of, or no practical way in any case, to compute, in principle there might be, but in practice there isn't, A, which is a rational number. So the Motivic coaction tells us a lot about relations between Motivic multiple zeta values, but it does not tell us everything. And this is one of the sources of this ambiguity of the map phi. The Motivic coaction simply cannot see this part of the problem. It's a regulator. It's no way of getting at it. So how can we compute A? Well, I can take the period of this equation, the period of star, and I have to go and travel into real numbers. So that, because we know this is true, typically it's true for actual numbers, and we get this. And so, in fact, I can compute A numerically, if you like. It's zeta 2,3 minus zeta 5 over... minus divided by zeta 5. So this is really... So this is some real number. You can compute thousands of decimal places. But we know that it's actually a rational number. And this is Borel's theorem. It's saying that there are no non-trivial extensions of Q0 by Q5 other than the one given by zeta 5. So this is extraordinary strength of the algebraic K3 calculation. So we know that this number has to be rational. Unfortunately, there is no rational way of computing this number, as far as I know of. So either using relations, and this is where the devil creeps into the whole Motivic side, because everything up to now has just been this combinatorial calculation, it just gives integers. But in the real world, these numbers can be very complicated indeed. So using relations or otherwise, we find out that A is minus 11 over 2. And this number is somehow sort of given to us by the gods.
You did know, but you weren't going to...
I did know it, yeah, but it's easy to compute this. Or using the relations that Herbert will detail next week. It's not too difficult to prove this. You know, prove this as a rational number. Of course, you can just compute this and find minus 5.49999999 and say, well, it's rational, so it must be. But that's the whole point. I pushed the difficult. The problem of identifying the rational numbers inside the real numbers is, of course, far more difficult than any of this stuff. So in any case, if you can prove this, if we know this relation is true on the level of real numbers in any case, then what we've done is we've proved it for the Motivic version. So this is an example of how we can lift relations between actual MZVs and they become relations between Motivic MZVs. So I've just done it. I mean, if we admit that we knew this relation with a -11/2 in real numbers, then by this argument, because we know A has to be is a rational number, it's uniquely determined, we've actually proved it upstairs in the Motivic model. And so finally, I'll stop here. I'll just give two examples of computations where you go the other way, where we can deduce results about about actual multiple zeta values from purely Motivic calculations. Let me just give two examples. They're kind of exercises. So the other way. So here's example 1. Zeta Motivic 2, 2, 2, 2, 2, 2. So this corresponds to something like this. And to compute the action of the Galois group, we want to cut out sequences of odd lengths. But every time I look at a sequence of odd length, it either begins and ends in 1 or begins and ends in 0. There's no other way to do it. Therefore, it's always going to give me 0 in this picture. So d2r plus 1 is always 0. And from the structure of the model U, for example, and knowing that this is an even weight, you immediately deduce that this has to be a rational multiple of zeta Motivic 2 to the n, where this is n. So in particular, you deduce without doing any work whatsoever that this number is some power, a rational multiple of some power pi. Second example, which is interesting because it has some history to it. You can look at 1, 3, 1, 3, 1, 3. And you say, ask why 1, 3, 1, 3, 1, 3? Well, so Donzagier conjectured that this was in a certain explicit multiple of pi to the corresponding weight. And it was proved by David Broadhurst a while later by writing this as a tricky hypergeometric integral and doing all these changes of variables and proving it that way. But I leave it as an exercise to do the same calculation, Galois theoretically, and you check that because of the combinatorics of 1s and 3s, that there's no way that these operators always act trivially on that. And so you get, for free, without doing any work, that this is a power of pi times some rational. Of course, there's no way of knowing. Motivic theory doesn't tell us what that rational number is, but it tells us by this sort of Galois argument that it has to be rational times power pi. So what we're doing here is really viewing Motivic multiple zeta values over Q as a transcendental extension of numbers, and I'm really doing Galois theory. I'm looking at elements here which are acted on trivially by the Galois group, so they must live down here.
What was the
So that's sort of the game that's going on.
one of the two has the one on the wrong side, I think.
One of the... Oh, yeah, thank you. It's the end of the day. 1, 2, 1, 3. Thank you. So that's it. That's really all I wanted
I was missing. Where did the pi to the 4n come from?
So we know... So if you look at the model U, if you look... so it's an exercise to check that the only elements who have completely trivial coaction, the only primitive elements of even weight are necessarily of the form F2.
It's zeta 2. Zeta 2 to the 2n's.
Yeah, exactly.
Okay.
So this is zeta 2, so I assume zeta 2 is pi squared over 6, of course. Sorry, I should have specified that. It's so ingrained. Sorry, it's hardwired.
The thing I missed was you were saying that was equal to some power of zeta 2. Therefore, the pi to the 3.
Yeah, so the same argument says that this is equal to a power of zeta 2 Motivic, and zeta 2 Motivic is pi squared over 2. So we get from a sort of a Galois theoretic argument that it's a power of pi, without knowing what the number is. So you can actually calculate with this. You can get some algorithms for doing this. And the point I'd like to make is that in this story, it's absolutely crucial that zeta 2 Motivic is non-zero. If zeta 2 Motivic was 0, this equation here would give us absolutely nothing. There's no way of computing B. And we'd have to prove, in order to prove something motivically, zeta Motivic 2,3 is zeta Motivic 5 plus, modulo something. You would have to do a computation in the world of real numbers in which you compute zeta 2,3 is a multiple of zeta 5 modulo powers of pi, which is completely impossible to do. So if you dispense with zeta Motivic 2, then this whole machinery is completely impossible to work with. So it's very important that zeta Motivic 2 is non-zero. You just cannot do these. The whole framework doesn't work unless you do that.